Hello everyone! Today I, Michael Yee, and my partner Mason Young will be presenting on ethanol biofuel production with integrated first and second generation distillation techniques, as well as possible biofilm inhibitors. So why ethanol biofuel? Well, we know today that energy consumption is rising and the demand for a sustainable energy source is rising as well. And we know that using the fermentation of organic matter, ethanol biofuel can be reduced, and it is a sustainable alternative. This is done by processing food waste or lignocellulosic organic matter, and we know that any improvement to current methodologies today in both energy or cost efficiency will be beneficial in both an environmental and economic scale. This is our take on ethanol biofuel distillation. By using the integration of both first and second generation distillation techniques, we can take advantage of using all parts of the feedstock. That includes the corn, in our case itself, as well as the stover, which includes the stalk, husk, and cobs. We will also be testing the feasibility of using a biofilm inhibitor while taking into account economics and practicability.
We're analyzing the feasibility of a biofilm inhibitor because normally during ethanol production, during the fermentation stage, contamination bacteria will build up as a biofilm in the reactor. Normally this biofilm must be removed by stopping operation, shutting down the tanks, and then manually cleaning them. However, it was discovered that certain enzymes will limit the biofilm buildup, circumventing the need to manually clean them. The Novozyme 188 enzyme specifically was found to be the most efficient. However, it's since gone out of production. As such, in this report we'll be analyzing the Celluclast 1.5L enzyme because it was found to reduce biofilm buildup by up to 85%, and it will resist denaturation at high temperatures.
With those considerations in mind, we drew our inspiration for first generation distillation from several sources, the first of which was an ethanol and distiller grain gum plant by Kurakowski et al. Specifically, Figure 1 was used as our baseline for designing our first generation process. Similarly, Anthony et al. Too also used Kurakowski et al. To produce a Aspen simulation of said process. This simulation was used as the baseline for our first generation distillation process and its stream pricing. In designing our second generation distillation scheme, we drew inspiration from a lignocellulosic ethanol biofuel distillation process by Aden et al. This reference provided extensive stream tables and process flow diagrams for the entirety of the process. As such, this became the baseline for our second generation stream pricing. When procuring the method to integrate the first and second generation distiller, we used a process flow diagram designed by Jolson et al. Putting all the pieces together, we came up with this finalized design. First, let's begin by talking about the first generation distillation procedure. Multiple reagents are fed into a heater, including the corn grain, and undergo liquefaction. The products of this liquefaction then enter the saccharification tank, where starches are converted into sugar. The products of that then enter the fermentation tank. We'll get back to that later after we discuss second generation distillation, which begins over here. Here, corn stover is pre-treated with sulfuric acid using a steam bath. The condensate of the steam bath is vented off as a liquid purge, and then the rest of the stream is fed into a heater, along with other reagents. This heater also undergoes liquefaction, and the whole process undergoes enzymatic hydrolysis, where long molecules are broken down into smaller ones. Lignin is then separated from the stream and burned for energy, and the rest of the stream feeds into the fermentation tank. Following fermentation, the product is siphoned off into a fractional distiller, where ethanol is distilled and liquid waste is vented off on the bottom. It should be noted that our enzymatic biofilm inhibitor is added over here in the fermentation tank.
Reducing our system to an input-output level gives us this graph and allows us to analyze the system on an economic scale. Unfortunately, we're unable to find pricing on the large scale for our raw materials and feedstocks, so we use the reference papers in order to find pricing for those streams. However, since those papers were written in the past, we use the Bureau of Labor Statistic values for consumer pricing to bring those values up to the current day and account for inflation. This does not account, however, for the fact that the markets may have changed since the time when the papers were written, so it's only an estimation at best. In order to reduce those scaling inaccuracies, we've kept the same flow rates as in the papers. Using these estimates, we were able to generate a table detailing the cost and the flow rate of the raw materials used in our process. The pricing of the biofilm inhibitor did not come from our reference papers, but rather from an independent supplier, Sigma Aldrich. After normalizing the cost of the materials to the present day values and factoring in the enzyme, we could tabulate the cost of the raw materials for the system. However, since the wastewater was so dilute, it was assumed that the treatment cost for it was negligible and we didn't include it. We were also able to generate the amount of ethanol product produced by this system and the selling point of the product. The price for this selling point was found from a competitor, the Carolina Biological Supply. From our tables, two important earnings were calculated. The first was the earnings of a 330-day operational year with and without the use of the biofilm inhibitor enzyme. The second was the earnings from a full operational year, assuming that the biofilm inhibitor allowed for 20 more operational days, because we would not need to periodically stop operation to clean the reactor tanks of biofilm. Sadly, due to the high price of the biofilm inhibitor, using Celluclast yields a negative profit for the system. It's worth noting, however, that the enzyme price was not based on the bulk prices but on laboratory quantities, since we were unable to find a quote from Sigma Aldrich on an industrial scale order. It very well could be that the bulk pricing would reduce the cost of manufacturing enough to yield a positive profit. In order for the biofilm inhibitor method to become profitable, we would need to sell the ethanol for a minimum of this price per liter, or if we were able to find bulk pricing on the enzyme for a maximum of this price per kilogram, it would become profitable. In addition, if we were able to find bulk pricing for this price per kilogram, it'd actually become more profitable than periodic reactor cleanings. Because the earnings were negative for the biofilm inhibitor scheme, a return on investment calculation is only practical for the process that did not use the Celluclast enzyme. With this in mind, assuming a 35% tax rate and a 10% rate of depreciation, a 10% return on investment is only possible up to a maximum TCI of this value here, also known as the break-even point.
It is always important to discuss possible design alternatives to your process. In our case, a very practical consideration can be the type of feedstock used in both the first and second generation distillation schemes. Some of these potential feedstocks include, but are not limited to, wheat, straw, or simply other grain types. Largely, this depends on the regional availability of your feedstock. Logically, you'd want to choose the feedstock that is the most readily accessible. In addition to that, another design alternative that we explored was using the power generated from the combustion of lignin from our lignocellulosic second generation process to power the first generation process, as well as potentially the distiller with the use of heat exchanging system. Ultimately, this will lower your overall energy costs. In implementing our design, there are several considerations that must be taken into account, including environmental, social, and safety considerations. Our process has the potential to be far more environmentally conscious than fossil fuels, due to it using a sustainable energy source. However, carbon dioxide is produced from the combustion of lignin. That being said, that carbon dioxide would have been produced regardless due to the simple nature of decomposition of the biomass. A potentially negative environmental impact is acidic wash water. Although it is very dilute acid, depending on your laws and regulations of your state, some neutralization may be required as post-treatment. An important social consideration is the fact that biofuel distillation as an industry can increase the demands for feedstock. This can drive up the price of said feedstock and also affect the market. Safety considerations are as follow. Ethanol is a Class B flammable chemical, and as such, you will need a fire detection and suppression system in your plant. Additionally, ethanol can also be corrosive in high quantities. The Celluclast enzyme, if implemented, is a strong aspiration hazard. You would need workers to wear masks when handling it to avoid danger. Fermentation can also build up pressure in the reaction tank. Pressure releases will be necessary to release built-up pressure, and material loss due to improper transport system can contaminate the nearby vicinity.
In conclusion, due to the extremely high break-even TCI at the input-output level for the method that did not use the Celluclast biofilm inhibitor enzyme, it is recommended that this project be pursued into the future. The environmental and economic benefits make it extremely desirable as a method of alternative energy production. Thank you, Boehner Chemical Corporation and Associates, for the opportunity to explore this design. Goodbye.